Welcome to this specialized research laboratory where extensive scientific research and testing are being conducted on an innovative and highly advanced braking device, which is a unique patented braking device. That's right. As well as the RSS-Hook retarder. This is a retarder, a decelerator, a vehicle speed stabilizer. The hub operates according to Hooke's law, the theory of elasticity, the tangential theory of elasticity. Here, instead of, in the case of a hydrodynamic retarder, where oil friction is used, and in the case of an electrodynamic retarder, where eddy currents are used, in this specific instance, neither of those conventional methods is actually utilized here. We are not talking about standard brake pads, nor are we discussing dry sliding friction, but rather a series of specialized elastic elements are employed instead, which are carefully mounted on the disc and are firmly pressed by pressure bearings, thanks to the caliper, in this case from both sides. This retarder is an automotive one. It should be emphasized that there is no retarder in the world, especially a mechanical one, for automobiles. Why? Because the conventional retarders that are installed in trucks to slow them down on long descents are very large in size, 10 or even 20 times bigger than this retarder. 10, 20 times bigger? That's why motorists believe that such large, massive retarders with a diameter of 80, 90 centimeters, about a meter, well, because of their bulky size and dimensions, it's simply not possible to install them on cars or light vehicles, and there's no point in doing so. We have successfully developed a specialized retarder based on advanced spring elements, which allows us to achieve significantly greater effects even with much smaller dimensions. There are, as you can clearly see, various braking torques involved here, and these braking torques can be either static or dynamic in nature. This design ensures maximum efficiency across all operational conditions. Dynamic braking systems specifically refer to those moments when the vehicle is actively moving on the road, and its kinetic energy is being effectively reduced by using either the primary service braking system, or, as we are seeing in this particular case, the auxiliary retarder. Here we are carefully demonstrating and analyzing the static braking torque. Since the static braking torque in a completely stationary and fixed position is the most critical and fundamental parameter that determines the overall braking properties of any given braking mechanism, which is, in this specific case, the retarder. To demonstrate this effectively, we have securely mounted the component on the shaft, exactly as it is installed on the vehicle. We have brought it here as it would be installed on the vehicle. We installed a lever 110 centimeters long on the shaft. So, due to the pressure for compactness, we use a manual hydraulic pump here, which creates pressure there 200 to 300 atmospheres, and it is transmitted through a hose that is through these oil channels. Each one, can you show from that side too?
Yeah.
Show me from that side. This means that this pressure is transmitted. This pressure is transmitted simultaneously and equally to both calipers. These are the calipers, cylinders, and then the pistons. They press the bearings. Next, we will show you the condition of the bearings. This is the device. It is pressed symmetrically on both sides by bearings, which is what produces a braking torque. This braking torque is static. By applying this pressure, we determine it by means of... To understand this process more clearly, for the sake of simplicity, we use standard mechanical dynamic scales and determine it accordingly. Here, for example, we take the specific number of kilograms that we obtain from the measurement, and then we multiply that figure by the force of gravity in newtons, and then by the distance in meters, which represents the total length of the lever arm. By doing this, we finally obtain the precise value of the torque expressed in newton meters. This is the main value. It should be noted that for heavy-duty industrial vehicles, the maximum effective braking torque output value for such large retarders typically starts at approximately 1,000 newton meters. Newton meters up to about 2 to 2.5 meganewton meters. And moreover, at low revolutions, it is impossible to even study the static moment in this way because at low revolutions, with minimal movement, it does not work. Why? Because in a hydrodynamic, let's say, retarder, the effect depends on the internal friction of the oil. The faster, for example, the friction occurs and the jet of fluid hits the walls, the more it allows it to stop. But in this case, if the speed decreases, it becomes almost impossible to stop it, meaning that creating a static moment is practically impossible. The same applies to eddy current brakes. Due to the fuel consumption in electrodynamic braking, to slow down by 15 to 20 kilowatts per hour, you have to supply, that is, provide a current of 200 ampere hours. That's how large it is. It heats up to 600 degrees, so it's often avoided. And there's the question of whether it can be installed on a bus or not. In this case, it's mechanical. It doesn't have any friction in the main part, no grinding, no friction in the oil, no friction. The magnetic UFO brake has no friction from magnetic fields, so it doesn't heat up at all. We studied this experimentally in this repantsaur. The references will be shown. There, the temperature rises by only 60 degrees, while in those, it's 600. And as for braking systems in general, if we're talking about them with you, as for temperature gradients, in a thermal brake system, it can reach up to 1000 degrees. Here, it's 60 degrees at most. Now, our executive director will show us. He'll apply pressure here.
Wait, to apply pressure, we need to level this lever. To level the lever, you need to apply a little pressure so it doesn't fall.
All right, go ahead, apply the pressure. What? We're going to do. Well, let's measure it from this angle. Basically, it doesn't make a difference. Let's check the pressure. Now that's enough pressure. This distance, do we have a tape measure? No. All right, let's measure the distance. Okay, please measure the distance. Step aside, let me have it. All right, let's set it up like this. This distance here is about 103 millimeters. Yes, 103 centimeters. Well, let's just call it a meter. All right, that's enough. Let's check the pressure. Here, we have pressure being applied. That's enough. No need to raise it any higher. Give me the pressure. What's the pressure there?
300 bar.
300 atmospheres. All right, then let's step aside a little. And you can come here and take a look. All right.
100.
Keep going.
140.
So having 100 kilograms, if we multiply that by the length of the lever, we get 1,000 Newton meters. That is, the braking torque for the car's retarder, is 1,000 Newton meters. This value is sufficient for a light vehicle, more than sufficient. If we take into account that for trucks, this value is for the electrodynamic retarder as well, it's 1,000 Newton meters and even more at very high speeds. And in our case, even when, as you can see, there's no speed at all, it still revs up. In this way, it's impossible to determine the torque statically with an electrodynamic retarder. We can do it statically, and that is an absolute value. The static torque is an absolute value that determines both the dynamic torque it will have later and the efficiency of this retarder. So, as it turns out, this experiment shows us that it has a fairly large static torque, which means we can already experiment with it on a vehicle. Thank you.